It's another Physics 142 video, and in this video I want to do an example of using Ampere's law. So I just wanted to briefly review that the idea of Ampere's law is sort of like Gauss's law for electricity. It lets us calculate the magnetic field in cases where we have high symmetry. And specifically, we wrote it down here. It says that if we walk in some closed loop around some wires through a magnetic field, all right, around current through some magnetic field, then that will let us find that the amount of current going through the loop is related to the integral over this path, all right? So let's do an example here. And so the example I want to do is I want to think about, well, what's the magnetic field around a long, thin wire that has some current I? And so what do we mean by that? Well, that means that if I, pick some spot, right, a distance r away from the wire, right, a distance little r away from the wire, and I want to know what's the magnetic field at that spot, right? What's the magnetic field right here, right? What is the magnetic field there? Well, I'd like to be able to calculate that. This is a good example for Ampere's law because long, thin wires have lots of symmetry, right? They have this sort of cylindrical symmetry that we'll be able to exploit. All right, so let's dive in and think about how we're going to do this. So I'm going to need a little bit more board space here to dive in. All right, here we go. We got a little more space. Okay, so what are the steps? How do we do this, all right? Well, just like with Gauss's law, the first step was to choose a Gaussian surface that exploited the symmetry and intersected with the spot that we care about, all right? Similarly, we're going to want to choose an imaginary loop that we want to walk around. All right, so here, I might want to walk in a loop that encircles this wire because that would be exploiting the symmetry of the problem, and I want to make sure that that loop has some radius r, right? Maybe this would be a little bit better to see sort of end on here, right? So if we think about looking at the wire from the end, so this is a wire coming out of the page now, right? My sort of, end on view. All right, so that's the wire coming out of the page. All right, the loop that I might choose here that exploits the symmetry of the problem is just a loop that goes around the wire like this. All right, nice circular loop. And well, why is this a useful or interesting loop? Well, we've learned before, what do the magnetic fields around wires look like? Right? What do magnetic fields around wires look like? Well, what we realized is that if you put your thumb in the direction of current, right, if you put your thumb in the direction of current, your fingers will wrap around the wire in the direction of the magnetic field. So magnetic fields wrap in circles around wires. All right, so here we could draw in some of what the magnetic field looks like. All right, I guess let's give this some radius r. All right, here's my imaginary loop with radius r. And so the reason I want to choose this, all right, is one, it's sort of a loop that's nicely taking advantage of the symmetry of the problem. And two, well, my magnetic fields, right, if I put my thumb coming out of the page here, right, my magnetic fields are going to wrap around this wire such that if I'm on top of the wire, the magnetic field is going to be going this way, right? If I'm here, the magnetic field is going to be going down, right? Here, the magnetic field will be going this way, right? And here, the magnetic field will be going up, all right? So we've got magnetic fields here, right? And the magnetic fields wrap around the wire, and so I want my path to also wrap around the wire. Okay, that will nicely exploit the symmetry of the problem. So let's maybe write this down as a step. All right, so step one is choose imaginary path. All right, so we're going to choose our path, and we want it to exploit the symmetry. And have sort of radius r, right? Okay, intersect the spot we care about. Okay, so that's sort of step one here. All right. Then the next step is to actually draw in our magnetic field. All right. So then we want to draw in the B field. All right. And the other thing we're going to want to draw in is we're going to want to draw in our little dl vectors. All right. Draw dl vectors, the sort of steps in our path, right? And to think about that, right, let's think about what Ampere's law looks like, all right? If we write down Ampere's law is that the integral over this path, right, the integral over this loop, we might say, of B dotted with dl is mu naught times the current enclosed, all right, times I enclosed, all right, the current enclosed in that loop. And so to do this dot product, I'm going to need to know my BL vectors and I need to know my DL vectors. So let's draw in some DL vectors, right? DL vectors are walking along the path. So if I'm over, on this side, my DL vectors are going to point straight up. There's one, right? Here my DL vectors are always tangent to the circle, right? So here my DL vector is going this way, right? Here my DL vector is going this way. At the bottom, my DL vector is going to the right, right? So there are a bunch of sort of example DL vectors, right? And DL vectors just go along the path tangent to the circle, right? They're the direction I'm walking at that point in time, or that point along my loop, all right? So now that I've chosen my imaginary path, I've drawn in my B fields, I've drawn in my DL vectors, now I can write down Ampere's law and evaluate, all right? So maybe we'll just put my next step here is evaluate, all right? And first we need to evaluate the dot product, because no one likes dot products, right? You want to get rid of those dot products. And so how do we evaluate a dot product? All right, well, what this says is this going to be the integral over this loop. What's a dot product? Well, it's the magnitude of B times the magnitude of dl times the cosine of the angle between them. So I go and I look along my path, and well, if I've chosen my path right with nice symmetry here, my b's and my dl's, they're always going the same direction, right? My b and dl's, they're aligned with each other, so the angle between them is 0, all right, thanks to that symmetry. And this is still equal to mu naught times I enclosed, all right? And, right, so cosine of 0 there. So that's just a 1, all right? And so that's all well and good, but I still can't evaluate this quite yet, except, well, there's a nifty trick that says that, well, if we're a constant distance away from the wire, right, if everywhere on the loop, it looks the same, right? Everywhere on this loop, because there's nice symmetry, right? No matter where I am, the wire is going to look the same, right? I'm always the same distance away from the wire. So that means that B at all of these spots has to be the same, right? For the same distance away, B is going to have to be the same everywhere around this wire because it's nice and symmetric, right? If I walk this way, it doesn't really look any different from walking this way. So B is constant everywhere along the loop, all right? So since the magnitude of B is constant, all right, now the dot product got rid of the vector, just left us with the magnitude of B now, right? So dot products get rid of the vector, just leaves us with the magnitude of B, it's the magnitude of dl, all right? So because the magnitude of B is constant, I can pull it outside of the integral, all right? So I should equals mu naught times I enclosed, all right? And this is because magnitude of B is constant over my loop, all right? So I'm only allowed to do this because I've chosen a nice loop where everything looks the same, all right, where the magnitude of B is constant. Well, now, all right, now all I have to do is I have to evaluate this path integral, this closed path integral dl. Well, and if you integrate over dl, what is that? All right, integrating over dl, that's just saying, well, how far did I walk, right? How far did I go around? Well, and so I can calculate that. If I have a circle of radius r, the circumference, the distance I walked around, is 2 times pi times r, right? So I can write this, right? This is just the total path I walked now, which is 2 pi r. So now we have B times 2 pi r is mu naught times I enclosed. All right, so we'll rewrite that. B times 2 pi r is mu naught times I enclosed. And so if I want to then solve for B, all right, just have to divide by 2 pi r, I get that B is mu naught times I enclosed divided by 2 pi r. Now I just have to check and say, all right, how much I is enclosed? Well, in this case, I was told the current has the wire has an amount of current I. That's the only current in this loop. All right, so I can just replace this I enclosed with just I, right? It's just, I is the total amount of I enclosed, right? How much I is enclosed? Well, just I's worth. Okay. I, yes, all right. So I'm almost done, right? This gives me the magnitude of B. What's the direction? Well, the direction is around the wire, right? As I've drawn in the picture, we know it goes around the wire, it loops around the wire as I've drawn in the picture. So that's actually pretty straightforward to use Ampere's law to do this evaluation. All right, once you've imagined your circle, all right, you just go ahead and take the dot product. I guess not just, right, but you take the dot product, you look for, hopefully, B will be constant, so you can pull it out of the integral. Then the integral will just be a path length, all right? And you can divide by that path length and then solve for the magnetic field. So we'll do a couple more examples in future videos.